All right, let's go ahead and get started. My name is Arvind Krishnan, and I work at GoEngineer as an applications engineer with a focus on 3D printing, SolidWorks simulation, Inspire topology optimization tools, and I work out of our Dallas office, focusing on a lot of this upper North Tola region, Texas, Oklahoma, Louisiana, Arkansas, and really happy to bring this webinar to you on lattice structure optimization, which is a new 2018 functionality in SolidThinking Inspire. Before we get started, a couple of housekeeping items. If you have any questions, please feel free to type it in the chat box, and we will definitely address them towards the end of the webinar after I get done. And this video or this webinar will be recorded and uploaded to our YouTube channel within a couple of days. So if you miss it or want to kind of go back and look at the whole thing, then this will be available at youtube.com/GoEngineer. So once again, today is about looking at an in-depth look at SolidThinking Inspire's lattice structure creation capabilities. So let's get started. To get you an outline for today, and we will start with what is lattice structures and what do they do, why are they used, and then we'll look at three specific scenarios. The first one, weight reduction. We'll go through an example together, and we'll look at how the lattice structure functionality can be used to reduce the weight of a design. The next one, let's look at osteointegration. The medical industry loves implants and wants them to be as lightweight as possible. And as long as there's biocompatibility and the bone accepts it, we'll talk about some more functionality there where the lattice structure will help bone ingrowth. And finally, while I was playing around with this and looking at a couple of examples from Altair folks, we ran into this new exciting application for weldment optimization. So that's something that we will definitely hit on and look forward to that. That is something I'm really excited about. And finally, we'll talk about what can we do with these results. How do we export it? What kind of options do we have? So yeah, let's start with an introduction. What is a lattice structure? In short, the animation that you see on the right, it's all those beam-like structures that's semi-hollow on the inside, which is what a lattice structure is. It basically helps connect the different regions of your structure, but is not 100% dense. Think of if you have regions in your structure where the stresses are not as high, your lattice structures are going to help you connect them but still keep the weight low. So Inspire is primarily a topology optimization tool, and I'll talk a little bit about that functionality as well. But one of the new features in 2018, and another one is overhang supports for 3D printing, which is cool by itself. But one of the new functionalities in 2018 is this lattice structure creation. The best part about this tool is that it is load-based. So you're not just adding lattice structures in any predetermined location. You're actually adding the lattice structures based on the computer algorithms, and it's looking at where your restraints are. It's looking at what the material is. It's looking at what the connections are, what the different boundary conditions are, and based on that, it is creating a lattice structure that is based on an FEA study or on a finite element analysis study. So you can also specify the amount of lattice creations by weight, what are its properties, and then you run the analysis. So starting from the shape that you see on the right, you can go ahead and set all of that up. And once we do that, then we can go ahead and create the lattice structures. Now, for something as complicated as you see on the right, in a lot of cases, 3D printing or additive manufacturing is going to be the best methodology to produce these. So let's go ahead and take a look at our first application. Now, this GE bracket is become very famous of late, and it's been used in a lot of engineering applications. So reducing the weight of our designs has kind of been the primary purpose of, has been a very primary engineering goal for a long time. And so based on that, what we're going to do is we're going to look at this GE example to tell you a little bit more about this. This GE bracket, they put out a design and they put out some parameters, some loading parameters. Where is it going to be fixed? What are our loading points? And it was initially, I think, 5 pounds. And the person who won the contest had about an 84% reduction in the weight. So we're going to use the same example, and let's go ahead and switch to Inspire and look at the setup of the study. All right, here is Inspire, and to start out with, I want to show you what the initial model looks like. Okay, so this is the initial model, and there's been a little bit of processing done. So first off, here's the Inspire interface if you're looking at it for the first time. Whatever you see in maroon is the region that the optimization study is going to be run on. There are some fixture points that are located in these 4 corners, and I see some loading conditions that have been applied. So we're going to go ahead and so this was basically used to produce this first shape using what's called topology optimization. And while I will talk about that a little bit, that's not the primary intent of this webinar. If you want to look, or if you want to learn more about the topology optimization functionality, there is a webinar that I did that is posted on our YouTube page. Another one that a colleague of mine, Tyler Reed, did. Those are 2 that I would recommend, because it goes through start to finish of how we started from that initial design to get to what you see on your screen right now, which is topology optimized and using the polynorms functionality. But this is going to be our starting point. So I'm going to go ahead and delete some of the existing parts. Okay, let's go ahead and delete some other stuff as well. And I have some loading conditions as well that I'll go ahead and delete, and then just start from scratch. Okay, so the first thing to do is a little bit of post-processing to our part itself, so that we define the region that we want our lattice structures to be on. I'm going to use this little partition tool, and I'm going to define the regions where I know my fixtures are going to be. And these regions I want it completely solid. So I'm going to say partition these and provide a thickness of 3 millimeters. So let me go ahead and switch my units real quick. Give me 1 second here. So let's go ahead and switch units. All right, and then let me turn on the partition tool one more time. And what you're going to notice is by a few simple clicks, I'm going to divide the existing region to these new parts that are 3 millimeters thick and offset from the faces, and then the rest of the assembly, which is my design space. So there you go. Now if I go ahead and hide the initial part, you see these. And then if I hide these, you're going to notice that they are automatically subtracted from the from the initial configuration as well, from the initial design as well. So let me do the same thing for my loading points as well. Here's 2 of the loading points. This time I'm going to use a slightly smaller thickness. Let's go 1 millimeter. That way I have a clear definition of my design space around the loading points as well. Okay. All right, now that we've done this, let me go ahead and hit the green check mark there as well. So if I hide the first one, I see all my loading points, and that's the geometry preparation, nothing too complicated. So, but the goal that I wanted to show you was how simple it is to divide regions that I don't want any changes to, or any creation of lattice structures to, and other regions. So for this specific, let me go ahead and turn that off. Okay, now that we're done with that tool, I want to make sure that I specify what my design space is. This design space is the region that is going to be optimized and lattice structures are going to be created on. So the rest of the regions that are in light gray are going to be completely solid. So now, like any FEA analysis, I'm going to go to my structure tab and define some key components. To start out with, material. Steel is the default. We have a point there that is where I'm going to define my load. We don't need that to be there prior, so I can delete that. Let me go ahead and continue with my setup. By default, everything is going to be bonded, so there's not going to be any movement between the adjacent faces of my different parts. Next up is my restraints. So SolidThinking has these very nice multi-option icons. So for example, this loading has my fixtures, it has my torque, it has my pressure, it has my forces. So I'm going to first go ahead and select my hinge condition, which I'm going to apply on all 4 faces. And right click to hit the green check mark. Next up, we have our forces. So I'm going to go ahead and select a force. And for this one, I want to actually switch my units again. So let's delete that force and switch back to English units. All right, forces. So we want a force of, let's say, 8,500 pounds. And now this force, I want to offset it to that central location over there. So I'm going to go ahead and move this manually. And once I do this, I can also specify the direction of the loading. I want to make sure this is pointing in the X direction, and that's the load. Now, this load is a remote load, if you're familiar with that term, and I want it to act on both faces. So I can go ahead and do that as well. So right now I have my loading acting on both faces. So in a relatively simple few clicks, we've specified what my loading condition is. We've specified the fixtures. We've defined what is my design space, what is not part of my design space. So the maroon region is going to be optimized. And I can define a few more loading conditions. For example, we can define a torque. Once again, I'll select this face and let's do 5,000. But I want to move that loading to that same central point, and once I do that, I want to make sure I specify it on that second face as well. Now I want to make sure that the loading condition is about the global z-axis, so I can go ahead and change the direction of that torque as well. Oftentimes you will have different loading conditions or different load cases acting on the same part. Imagine a bracket that's loaded in the X direction, the Y direction, torque. So what we can do is we have the ability to create multiple load cases as well, which is what the load case does. And in this case, we can also specify a specific load and which load case to include it in, and which one to exclude it from. So for example, your support might be included in all the different load cases. So we can just come into the different load cases and make sure that we specify that these supports are included in all the load cases. Once we do this, let's go ahead and talk about what our run options are. So keeping in line with our FEA terminology, in this little run option, we have a bunch of sub options here. So first off, what type of study do I want to run? Do I want to do a topology optimization, which is basically going to go to that maroon region and try to remove as much material out of that as possible, and only keep the regions that affect my stiffness the most. Topography, gauge, and the topography and gauge options are typically used for thin sheet metal-like or surface-like geometry, where you want to add ribs to critical regions to increase the stiffness of it, but make sure that the design is as light as possible. So that's what those next three options are. And what we are going to do today is use the lattice option in the bottom. It might have been evident from the workflow, but I do want to emphasize that you do not have to do a topology study before you start your lattice structure analysis. We could have directly done the lattice structure optimization in the initial geometry that I had, but in this case I did do a topology study before and used that geometry as my new starting point before we went ahead and ran the lattice structure study. So let's look at some of the parameters in our lattice structure analysis. The first one is target length. This one basically describes how long each of the lattice structures are going to be. Then you have the minimum and the maximum width. The solver is going to use these numbers to determine whatever regions have a higher amount of stress because of the geometry and the loading conditions. It's going to try to use the higher diameter on that, and the regions that have lower amount of stress, it's going to use the try to use the lesser minimum diameter value to it. And lastly, we have our fill width. So you can use 100% lattice, 90%, 80%, or go even lower. And finally, what is the goal of the analysis? How much mass do you want to remove from the structure? So we can remove anywhere from, keep 5% of the volume, 10%, 30%, or I can choose a custom value and go ahead and put in my own values. Since you're removing mass, you're going to decrease the frequency of and the stiffness of this part. You can also specify the maximum frequency that you want or the minimum frequency that you want, below which you don't want to go. If you're used to FEA functionality, typically you're wondering, where is my mesh? There are some options to change the mesh size for each model by going into the property editor for each part, but the automatic mesh option, which is what's used by default, when we run a lattice analysis, it's going to create a beam element and it's going to use that target length as the beam element length, and then the cross-sectional properties of the beam is going to be determined by the diameter it uses. So that's the thing that it's trying to optimize when we run the study. Now, ideally I would have gone ahead and hit run. I believe this study takes about 10 to 15 minutes, so I'm going to go ahead and open up a model that I already ran before. So I'm not going to save this, and what we're going to see is in this model there were 4 different load cases, and let's go ahead and look at these other forces as well. So you see 3 forces and 1 torque, and then this is what was ran. So let's go ahead and look at the results real quick. Like any FEA program, this is the entire FEA results that you're looking at. Once again, we did not request 100% lattice, and hence there are regions here that have a relatively higher stress where it's kept the entire solid model and not removed material from there. Whereas there are other regions where the stresses are relatively low, where it's gone ahead and tried to remove as much material as possible. So what I want you to note is, as you look closely at the structure, is how there's regions where the density or the diameter is relatively bigger, and then there's probably other regions here where the diameter is relatively smaller. So once again, it's a load-based study. It's a load-based lattice creation algorithm, which is just phenomenal. Now, keeping in mind this is an FEA tool, and we've got some results here, so we can actually animate how this looks. I can go ahead and maximize or increase or decrease the deformation. Of course, this one is magnified so that we can actually see with the naked eye what's going on. Here are my displacement results, right? Regions that deform relatively lower, there's some regions that move a lot. And I can look at this for each of the different load cases. So here's the torque load case, and you can see how it behaves for that. Keep in mind the optimum shape is for all the different load cases included, and not just for one of the load cases. Okay, so I wanted to make sure I talk about that functionality. All right, so here's the 4 different load cases, the results as we see in our screen. And this was the first application that we wanted to look at, which was reduction of the loads, reduction of the weight, taking the loads into account. All right, let's go ahead and continue. Next one is osteointegration. There's been a lot of medical applications where a good surface with lattice-like functionality helps in the bone growing into it. So we want our implants to be as light as possible when carrying loads that are imparted by the human body during motion. But there is a secondary reason for having lattice structures and in the implants, and that is for osseointegration. So once again, it refers to the integration of the implant into the bone, and when this happens, you're creating a good bond between the two, which means the implant would last for a longer time. So what we see on our screen right now is a mandible or a jawbone implant. I have 3D printed this using our PolyJet machine because of the fine, intricate details that we see in our screen. Another benefit and another reason why I did it this way was we have dissolvable support, so that I don't have to actually manually remove all the support from those lattice structures. I can just throw it in a tank and dissolve it away. So let's look at another example. This is a hip implant. Roughly 800,000 hip implants are done every year, and a crucial design requirement is to make sure that the osseointegration happens well. So according to some research that folks at Altair and other companies and other doctors have done, there is a optimal size for the lattice implant that you would need, that is preferred for bone growth, and in that case we can use those exact parameters to create our lattice structures for the hip implant. The picture that you're looking at in your screen right now, that's from an FDM print, fused deposition modeling, or filament fabrication methods. This was a relatively larger print, and hence I could use an FDM print, which gave me better stiffness and better material properties as well. So let's go ahead and switch to Inspire and take a look at this. All right, so let me go ahead and open that up. All right, so here is the femoral stem. And once again, you can specify what your design space is. Considering we've already done one study, I'm going to go ahead and look at the results. of this one and talk about how that ran. So let me go ahead and pull up the results real quick. Let's see, I think it's this one. Nope, give me just 1 second. There you go, that should be it. All right, so as you expect with this implant, based on that loading condition, you have regions in compression and then regions in tension. And wherever the stresses are relatively higher, you see a more thicker lattice structure, a more denser lattice structure. And then in other regions where it's relatively thin, you see the lattice structures are more are less dense. So just wanted to point that out. So once again, amazing functionalities right here. We can look at different types of results based on the lattice structure thickness itself, and then what is the distribution of the diameter. So a lot of different options available. All right, let's look at the third application for today, which is weldment optimization. So this is one of, in my mind, the coolest applications because it opens the door for a wide-ranging audience to use this tool. If anyone's used the weldment feature in SolidWorks, typically the way we do it is we go ahead and design the weldment, and sometimes some people might go ahead and validate those designs using FEA, and we might make some changes depending on the FEA results, and then we test the weldment to make sure that everything looks good. But where is the optimization? How do we know that that's the best design that we have? So there's a lot of tribal knowledge that goes in to work when we do this, and while that's amazing, there's also room to optimize our designs in such cases. So I'm talking about weldments, but what you look at your screen right now is a complete solid model, right? So there's a new process, a new design process that I'm trying to define here. So the first step is for me to completely fill in the entire space that I want my weldment structure to be in. And once I do that, I can then go to Inspire and define that region as the region that I want to optimize using Lattice. And once I do that, I can specify my load. So imagine someone sitting on the top, which is what that vertical load is on the top. You have your wind loads, you have let's say the different wires pulling and pushing the structure, which the loads might be relatively lower, and then you have your fixture points in the bottom. So what we're going to do is let's go ahead and go to Inspire and look at this very structure. I'm going to close this existing model and open up my cell phone tower. All right, so here is the cell phone tower, and or an electricity tower, right? So you have your fixtures in the bottom. Again, keep in mind there's multiple load cases that I have defined. The objective here is that all of these may not happen at the same time. If you think it does, then you can apply all the loads together, right? But this is the entire model, and what you see in maroon again is the design space. So the same lattice structure functionality was used, and what I thought would be an ideal length for each of these beam structures is what I have defined as my target length. Let's go ahead and look at some results. And this is just amazing. So here we have optimized the weldment profile that we want, and you're seeing some regions where it's going to be relatively thicker, and you're seeing other regions where there's less weldments owing to slightly lower stress results. So once again, you're taking your loads and different fixtures into account to determine what's the best placement for lattice structures, right? Think of architectural models where this might be useful as well. A lot of architectural designs. I think there was one in China one in Malaysia, where there was an air bridge that was built based on topology optimization results, and a lot of architectural models, and now we can do Weldment structures as well. So this is truly amazing functionality. Now, how do we make sense of these results? So here is what we had, and then these are the results that we got. So based on this, we can go ahead and take inspiration from that and go ahead and create results or create the same thing in SolidWorks. SolidWorks is the package that I use. Once again, using Weldment profiles, there's a lot of details that we can do here. So now we can use that inspired design as inspiration for coming up with this design. But it also, and you can see all my different Weldment profiles here stacked up on the left. I should thank my colleague Tim Strange, who helped me. Who helped put this together. So having said that, the next thing I want to talk about is actually exporting our results. So how do we export our results? Inside of Inspire, there is a functionality to export these lattice structures and the entire design, including the non-design space, into an STL file that can then directly be printed. Now, there are a couple of options. One is a lattice export, and another one is a smooth lattice export. And I will talk about what these two mean, but to just give you a rough idea, the lattice export for one of the structures that I did created a file size of 10.4 megabytes. And the smooth lattice export, which creates a better transition between my different lattice structures on the insides. So you're looking at a triangular element that has to be placed in a lot of these curved features, and that bumped up the size by about 20 times. So now where that functionality is for those who already have access to this, once you're looking at results, you can either do the smooth lattice or uncheck that and then just save the file out as an STL. So those are your two options to export the results. Or you can take inspiration from your results and then go ahead and create your own models in whatever CAD tool you used. So once again, wrapping up, we spoke about what is lattice structures, and we spoke about 3 specific scenarios where it would be useful. One is just weight reduction. Typically the shapes are complex enough where you might want to look at additive manufacturing as a methodology. Another one is osteointegration, where a good surface lattice is going to better help bone ingrowth. And finally, the third one was Weldment optimization, which is new, which is exciting. It's something that's not been done often before. And it's really functionality that we can use to decrease the weight of our designs without, but making sure that our factor of safety and other important constraints are taken into account. And finally, we spoke about saving these results, either taking inspiration from them or saving them as an STL file. So once again, my name is Arvind, and thank you. Thank you for joining us.